Okay, let's get started. Eldad, get your whiteboard markers, and let's get started with this session.
Hey everyone, thanks for coming online.
Are you ready for some serious whiteboarding, Eldad?
I'll try my best. I give it a try.
Okay, so we wanted to do some, to pick your brain on tech, which you love so dearly, and try to explain to our audiences a few of the core concepts that Firebolt is built on. So let's start with the basics. We all know that at the core of Firebolt lies an amazingly fast query engine, but we want to dive a little bit deeper. Can you explain what you figured was missing from today's query engines in the cloud, and how Firebolt's approach to storage and indexing brings it to those really faster levels?
So I think maybe the biggest change and the biggest realization that not just I had, many people in that domain, which is big data, is that there is a love-hate relationship between storage tiers. So we're used to have fast storage serving analytics. Now we find ourselves with data lakes, having cold storage, needing to mitigate between cold, hot, doing tons of data movement. Analytical queries are complex by nature. They need to scan tons of data. And the first thing we thought about is how do you come up with a new format that is designed to be multi-tiered, designed to be fast on S3 and super fast on hot storage. And that's kind of where the journey started.
Okay, so you promised some whiteboarding. Maybe that's a good opportunity to start with. Tell us a little bit about that storage format, what it's all about, how does it work? I made sure the whiteboard is empty, so go ahead.
Okay, so Tamara, can I remove this beautiful picture? Thank you. So let's start with some serious whiteboarding.
Such a shame. It was such a nice painting.
So let's start with the basics. Let's draw a table. Call it T1. So this would be our logical table. It has rows in it, and it has a constant flow stream, so it's always growing. The first step to understand about FFF, that it's basically a way to represent a logical table. A logical table is a set of many FFF files, or more precisely, of FFF folders/entities. Each FFF file is responsible for managing its own domain, meaning that it has its own indexes embedded in it. It has everything it needs to serve data. So if we chunk up this logical table into smaller FFF files, then we would get multiple files being generated. Each file will get a different slice of the table. The way it works is you create an external table. An external table is basically a way to view your data source. It can be Parquet, CSV, JSON, it can be any format. It can be a Kafka stream. The important thing is that that's how we move data into Firebolt. So when you're doing an insert into select from external table, you're basically going through a process where you fetch your original data, let's say Parquet files. So we have S3, and in S3 we have a bucket, and in it we have many files. Those would be our Parquet files. When we start ingesting, we start convert those files into our own files. The important part of FFF files is that FFF is ordered and indexed inside the file. So we would have a bunch of new files being generated, but unlike Parquet, each one of those files will be ordered by a primary index. What is a primary index? A primary index is a way to say, if this is my logical table and I want to order my data based on those two fields, then what Firebolt will do is that every FFF file that's being generated will look something like that. So actually the first one is pretty ordered. So it is kept as it is. That would be our first file. The second file will look like this. Sorting is hard. And then the third file would look like this. So what we did was actually sort the data within the file. So now the data is ordered and each column is dense. On top of that, we add a sparse index. Sparse index is a way for us, we'll touch that later on in more detail, is a way for us to get a specific range based on a specific predicate. In our case, if I want to get all ones, then we need to scan each file and figure out if it has one in it. Instead of doing that, which is expensive and therefore will require us to download the whole file to figure out whether the data is in it, what we do is we ask the sparse index, tell us where one exists. And this is what we'll get. Let's go a few steps backward because I think I jumped a bit too fast forward, and first understand that AAA files exist in S3. So if I fetch data from S3 in a Farkash format and I ingest it through Firebolt, Firebolt will end up pushing and committed the same data in FFF back to S3. This is important later on as we go and discuss elasticity.
But in terms of the indexing itself and the sparse indexing, that's completely abstracted for the users, right? The users do not have to deal with it.
Absolutely. Users should not know what a sparse index is. They will never have to deal with it. The only thing user needs to know is the following, is that when you create the following table in Firebolt, T1, and you have those three fields in it, you want to find a primary index. And that primary index, in our case, would be based on F1 and F2. But that can grow into hundreds of fields. You can basically add all of your table's fields into the primary index. You wouldn't necessarily want to do that, but there's a big advantage into adding more fields into the primary index because every field applies ordering and every field applies indexing. So the more fields I'm adding, the better I will be able to apply ad hoc analytics on top of it later on.
And where are the indexes? Where and how are they stored?
So a more precise way to look into FFF is to actually think about FFF as a folder. And the folder has different tiers in it, different types of things in it. The first thing, of course, is the data. The data within a folder is a set of column chunks, like vectors. So if we slice the original table, the first file generated 4 rows, we will have 3 columns, each having 4 values in them. Those will be ordered, just like we described here, compressed and coded, and then this will be the data. And then we have a big family of indexes to support them. So sparse indexing is not really one index. It's not really one physical entity. We refer to sparse indexing as a set of indexes that combined together get us the range scans that we're looking after. So the indexes can be many types of indexes there. Some of them are at column level. Some of them work on a group of columns level. Some of them make sure that you can navigate forward. Others make sure you can navigate backwards. Some of them get born after you get the data in. Some of them get born while you fetch the data in. It's a living thing, and it happens in the background, mostly hidden from the user. The important thing is that those indexes are tiny compared to the size of the data. So you can easily get to kind of a 0.01 to 1% index size on your data. And this can scale, of course, to petascale. It is crucial for us to have indexes that efficient and small so we can use them in our compute before we touch any data point.
So what kind of queries benefit from that the most compared to sort of other query engines?
So for us, we really wanted to start with what we believe is the biggest problem with data warehousing, which is the last mile. So Last mile means serving the data, serving it to users, serving it to BI tools, serving it to custom-made apps. It's when you really want to turn the data into something that serves your product. It's less about insight. It's about really supporting your production environment with constantly ongoing queries running on top of it. What makes those queries unique is that they have two extremes. One extreme is those could be point queries. So you could have queries that are looking for a very small set of ones in a very long list of numbers. The other type of query is that you have big scans. So if I want to know who my top 10 customers are by sales over the last 2 years, I basically need to scan all of my customers, all of my sales, and then figure out which of them is top 10. So those two types of stream make analytical and data warehouses extremely inefficient, and they're not really designed to cope with those type of queries. We wanted to give the data warehouse the ability to really be able to serve those type of queries in sub-second. So in SQL, that means whenever you have a where expression or a join expression, that is when Firebolt will shine the most. So if you have complex where predicates, if you have many reports or dashboards or apps that constantly need to filter dynamically in an completely unpredictable way, that's kind of the first use case. The second use case is when you want to join, is when you have a star schema or a snowflake schema, and you have those big, chunky, fat joins that happen between multiple fact tables. Both of those operations would be heavily dependent on indexing, on sparse indexing, and that's how you go from minutes and hours to seconds.
Awesome. But okay, so a fast query engine is one thing, but when you set out to build Firebolt, you also realize that just being fast is not enough. It has to be coupled to a very flexible and super elastic architecture, and that's why Firebolt was built on decoupled storage and compute. But can you explain how Firebolt's architecture works together with those concepts that we just talked about, and what it allows customers to do?
So you have to repeat the whole question because I didn't get any of that. I was busy just drawing lines.
It was such a good question. I repeat it. So I said that we're fast and you built a fast query engine, which is great. But you also realized, starting Firebolt, that just a fast query engine wouldn't be enough unless we couple it with a really great architecture that's super elastic and flexible, and where compute and storage are decoupled. Can you talk a little bit about the challenges there and how that connects to the concepts of triple F that we just discussed?
So the second part of triple F is, as I said, is to deal with this tiered storage. So usually most cases looks like that. All of your data is always on S3, and then you spin up compute. Different products have different capabilities in elasticity. When we talk about elasticity, we always refer to isolated, disaggregated elasticity. That means basically one thing, that you can do two things. One is you decide the size and the amount of money that you pay when you spin up compute. So you can spin up a $1 instance. It doesn't matter what the size of the data is. You spin it up, you do something with it, but along the way, there are many of those coming and going. So your 5-minute ELT will use one type of compute. By the way, we call those compute engines. An engine is basically a cost unit for compute. So you have an ELT engine being spinned up every 5 minutes to ingest. That will probably be a bigger engine. Why? Because you're generating hundreds or terabytes of data every 5 minutes. Another engine would be a data scientist coming to work, wanting to ask some questions, wanting to run some queries, wanting to play with some models. Those would usually play with a subset of the data. Now, this is not about a subset. This is about querying a subset of the data. So what they need is spin up compute, cheap. I shouldn't pay more than that. I should be able to run my query on the last few weeks or apply some predicates on my query and then move on. When I spin up, consumption starts to work. When I stop the compute, consumption goes away. And this goes on and off all the time.
But all of these will work on the same copy of the data.
Yes, create engine. This is a SQL statement. So we wanted to have resource and compute embedded in SQL so people can write complex scripts and complex expression utilizing compute in an efficient and in granular way. And the important thing with isolated elasticity is that it's always on the same data, but more important, it's always consistent. So it doesn't matter where you're inserting data. It doesn't matter where you're creating the data. All of the compute resources are looking at the same thing. That is absolutely unrelated to the core efficiency, columnar vectorized, HPC, whatever. It is around being able to spin up thousands or more compute instances fast and have them all work on the same data.
So unlike the good old days where we had a giant compute or server or storage and compute are coupled and everybody's competing for resources, here I can throw any workload or set of queries at a different kind of compute resource with a different size and cost. But all of them will work in harmony as whoever inserts data, queries, everything will be always consistent.
Always. And yes, you're not moving your data. You have one data lake, or you have one bucket with everything, and then you spin up different resources to serve different use cases. So a classic example would be you're building your customer-facing product. That's your business. But then you have 10 features. Each feature has different SQL running. Each feature serves a different use case within your app. You want to have each feature being tuned perfectly for the use case. So if that's about chart 1, I would engineer or I would spin up compute to serve chart 1. If that's about query 2 to 10, I would spin up a different compute for query 2 to 10. So as an engineer, I'm basically mapping my production features that are data-driven into compute instances or compute units. So I can look at the whole picture and I know how much I'm paying per feature. Not only that, this compute resource will optimize itself for that set of workload. And this is all happening for you.
So can you elaborate a little bit on the data movement or how does the local storage in each such compute resource work and figure out which data from S3 in the AAA formats to fetch and whether that's interesting from a performance perspective?
Yes. So before I show you how that works, there's something important to mention here, which is sparse cache. So in most products, there is you need to define some kind of resolution on your data. Usually that comes as a file, a micro partition, a partition. There are ways to say, okay, this is my smallest unit, and when I want to scan data, I need to fetch that unit. It can be a packet file, I don't know, 200 megabytes. It can be micro partition, maybe a bit bigger or smaller. It can be a whole big partition that has tons of data. So, and each product has its own thing. The problem is that those files, they're huge, they're big. So if I had to download those files each time I need to figure out if I have ones in them, my query would be slow. I would never get sub-second. Usually when you do analytics, a big part of your query is actually scanning not that much data, but you need to scan much data to figure out which rows belong to the query. And if you're usually using pay-per scan products that charge you for the amount of scan you need to do to answer a query, that's when you really see that. Because you might run a simple query that has a where predicate in it for ones, and ones are 1% of the data. It will need to scan the whole column and basically download tons of files just to figure out that you need 1% of the data.
And when we say download, we mean copy it from S3 to the local storage
so you
of the
basically
compute
copy
resource.
the data from S3 to your local storage, and in many cases this ends up as spilling, and you end up choking your cache, and that's when the vendor says you need to increase your compute, which has nothing to do with compute. It has to do with the fact that if a file or a micro partition or a partition is your smallest unit, then you just fill the cache with unnecessary data, unneeded data, irrelevant data, noisy data that will never be used for querying, but it's there because it's within the same file, and this is compressed.
So what does Firebolt download?
So we don't want to download files. Our granular unit is a range. A range. Let's open the file. This is our. Let's say this is our file opened. A range is basically saying select F1 from T1 where, let's do a count, where F1 equals 1. Let's take that simple, oversimplistic SQL. So what Firebolt does is it basically runs two queries. The first query, and this is all hidden from the user, but the first query runs against the index. It's the same SQL, it's a query engine. It goes through kind of the whole set of steps, but then instead of running and getting data points back, we're getting ranges back. This is what we refer to sparse indexing. Sparse indexing means that if I'm having this predicate, Firebolt will tell me in those three FFF files, those would be the ranges of 1. So I'm getting 3 ranges, each one giving me a different offset with a starting point and an ending range.
So you're copying ranges, which means smaller parts of the bigger files from S3 to the local cache.
It can be 1 kilobyte, which is not good for S3, but it can be any size. It can be very small, it can be huge, it can be gigabytes.
But at the end of the day, we move much less data this way because the sparse indexing tells us only the right ranges.
It's not just that you're moving much less data. Your cache will only keep the ranges, meaning that we don't need to move 20 files into the cache. We just move 3 ranges into the cache. So this is where your kind of order of magnitude drop in cache size happens. And this is an absolute must because you're never going to be able to have your cache supporting your whole data set. In most of our use cases, this is exactly the situation. You're having a huge table, and then you have thousands of queries running, each with its own predicate, accessing very small percentage of the data. By the way, if the scans happen, there's a whole different domain of aggregating indexes and other type of indexes that solves that. Basically, this is where it all starts. So if you want to analyze last 3 months over those type of customers with that type of range of sales, then Firebolt will be able to kind of slice it perfectly together and give you the exact set of ranges that represent the predicate tree of your query.
And this remains true even if I use engines they could be small clusters and it could be huge clusters. And it's all managed.
Yes. The best way to fill it is to spin up a $2 engine on a petascale table. You can also do it on a terabyte scale table, and run your analytical query. Run this query that has those predicates in it, where you know from other products, just you know how much they scan. You see it. We tell you. They tell you. Everyone tells you how much you scan, and then you see that instead of scanning terabytes, you're scanning gigabytes. Sometimes people ask us, what is that 20 gigabyte scan? The data is so much bigger. How come you manage to scan so little data? And that's the answer. We work at range level, and this is why we need to order the data. So in many ways, ordering is the foundation for everything. Ordering is not clustering. We'll touch that soon. But once you order the data, you get this dense range of values, and then you can build sparse indexes on top of them, and you can make them efficient. And for us, efficient in indexing means that we can fit them in compute, and we can do that instantly. So when you spin up something, we want you to have access to the whole data, meaning that you need access to the whole index of the data, meaning that the index needs to be tiny, tiny, tiny. And that's a big chunk of kind of the effort that goes into tiered storage and FFF. It's not just what happens in S3, it's actually what happens in the cache. So in many ways, FFF is polymorphic because the way it looks physically in S3 is very different from the way it looks in cache. And that happens without the need to decompress and compress again. And so we need to be able to store those ranges and have a blast of a speed when you query the cache. So FFF changes. It starts when you ingest as something that is usually dependent on what you ingested. If I'm inserting a 1 GB per cat file, we will generate a 1 GB per cat file. If I'm tickling rows, okay, then we will generate those tiny little one file row. But FFF has another goal in life. It wants to marry other FFF files. It wants to merge with others. Merging with, it is romantic. It's a beautiful story because the more it merges, the better the better it feels in S3. Because the more you merge, the bigger your compression potential becomes. If I can get more ones into the same file, the better I will be able to compress it.
And that's the background process.
Yes, and it's completely different from how clustering works. Let's not forget, we don't have to have all ones in one file. We can have a one in every file, and Firebolt is able to scan millions of those files and get you all the ones in a split of a second.
Maybe let's use clustering to talk. That's an interesting point. I think it relates, if I'm not mistaken, to how we work with aggregating indexes, which is also an interesting topic in Firebolt, especially compared to materialized views. Can you maybe talk a little bit about sort of how Firebolt took a different approach compared to the classic materialized views approach, and how that relates to clustering versus?
So without getting into specific products, each has its own twist. But basically, when you cluster data, you're saying this file has a range of values it needs to contain. And then when I cluster my whole table, I'm generating those files and saying, okay, this is 1 to 10, this is 11 to 20, this is 21 to 30, and so on. Let's say we clustered by F1, okay? Nice, perfect. Yes, I spent tons of time on generating, but it's there. The problem starts when you start changing stuff. And mostly when in changing, I'm not even talking about updating or deleting. No, I'm talking about inserting new data. So let's say I'm inserting 10 new rows. Each row has a different value. And by accident, each row belongs to a different range. So basically what it means is that I need to rewrite all of those files to have the new 10 rows in each one of them. So if I have 10 rows, I can easily get 10 new files being rewritten just because each of them needs to now have this new one. With Firebolt, you never do that. Merging is something that's completely decoupled, isolated, both on the elasticity and on the snapshot level. And each file can have any value. It can have any value it needs because of sparse indexing. So our assumption is we don't want to touch those files. So now we're added 10 new rows. This is what we'll have those 10 new values in it. So the new file gets instantly generated. It's instantly available. It's instantly indexed. So the aggregating index, it's immediately committed together. And we never need to rewrite those files. The only situations when you want to rewrite a file is when you want to merge it. And that is decoupled from your ongoing experience. That is why, like one of the kind of first things that people notice with Firebolt indexing is that it's not being maintained. You don't need to reprocess it. You don't need to recluster it. I mean, if you can't cluster your materialized view, it's useless. If you can have high cardinality in your materialized view, it's useless. And you can't apply clustering on high cardinality. This is why, because you need to have those files with those specific ranges, and whenever you add the same value, you need to update those files. This is why people feel frustrated when they have no predictability into how long and when and how much it will cost to maintain their materialized views. With Firebolt, you get real-time. Aggregating indexes are never going out of sync. So you don't have a situation where it's not consistent. You change the data, it gets impacted immediately. And most importantly, you can have any size of cardinality in it. It's perfectly fine to have 100 billion unique values in Firebolt because every file will have its own sparse indexing, mapping the ordered, sorted, clustered values within the file. So instead of looking at the table and saying this table is clustered, the way Firebolt looks at it is saying each file is clustered or ordered. This is how you get aggregating indexes, replacing materials used, and becoming something that you just don't think about anymore. The only thing you need to do is to define them, and actually we're also kind of thinking about that. Like, do we actually even need to define those aggregating indexes? The answer is we don't. But right now with Firebolt, we basically opened up for you all the features around indexing. So you can create them, you can play with them, you can twist them, but know that over time, our interest is to avoid you needing to do that. Highly recommended to try it out. And usually what we do is we say, let's take a count distinct on your, on your landing pages. Let's do a group by on, a few tens of billions of keywords and sites, and let's have that as an aggregating indexes. Nobody will even consider doing a materials use solving that. And this is very unique for Firebolt, and this is all designed for one thing, to serve analytics, to do the last mile.
Awesome. I think that's been amazingly interesting. I do want to maybe switch to actually questions that we see here in the chat from the audience. We didn't talk about clouds in general. Currently, Firebolt is on AWS Only. Does the way Firebolt work with storage, people ask, is it different, or will it work as we expand to other clouds, or is it an AWS specific thing?
So we should think about it in two ways. One is the market, and the other is expanding in the market. For us, AWS is everything now. We truly believe that AWS today is where the biggest and the most impactful data lakes exist. We've seen that. Most companies run their data lakes on AWS. Most companies generate their data on AWS. And that's where we wanted to start with. We wanted to we wanted to go after where the biggest problem exists. You will not find as many of those use cases on different cloud platforms at that scale. On the other hand, many companies, they are having a multi-cloud strategy. So it's not about supporting one or two, it's more about supporting all of them together. And that's something that's super interesting to us. So from a go-to-market perspective, AWS for us is king, and we're going to stay there. We actually believe that we have so much to give for that ecosystem, and in many cases, even preventing them from moving out. But as we go along and we start working with companies that just have a multi-language, multi-cloud culture, and they want Firebolt to run on datasets that get born in other cloud vendors, we will eventually need to support it, but that is not planned for the next 12 months. So if you need a multi-cloud strategy for a data warehouse, unfortunately, it will have to wait a bit. We're just too focused on making AWS shine and making data lakes in AWS shine. In terms of the stack and in terms of architecture and tech, everything is decoupled. So we're actually not using, aside from S3, we're not using anything on AWS. So all the stack can be moved over to any cloud vendor. Yes, it's a huge investment and effort, but we don't need to reinvent the wheel. So consistency, elasticity, isolated elasticity, the whole database engine, everything is totally transferable. I just don't think it's the right time to do that.
Okay, great. Another question we see here is whether I can install Firebolt
on your laptop
in my VPC, or whether it's SaaS only.
So Firebolt is SaaS. Our users, they don't maintain the stack. They don't need to maintain the infrastructure. But I can say that by the end of the year, we're basically done with all the compliance. So you shouldn't be worried at all. And in fact, I think if you think about BigQuery, Snowflake, and all of those vendors, that it's the same thing. So we haven't invented a new thing. We basically took what other amazing companies did before us. And maybe Snowflake would be the perfect example. So with Snowflake, you move the data into the Snowflake environment. It's S3, it's totally secure. And I think you mostly get benefit from it. Yes, there might be some companies that have that as a must. They have to have their data within the internal network, and that is not for Firebolt. So you need to trust us when you use us, and I think that's a fundamental feature of a cloud-native data warehouse, to be able to securely protect and handle your data. You're not just trusting us with your compute. You're not just saying to us, I want to crunch data with you. You're telling us, I want that everything embedded, hidden, transparent, simple, abstracted. I want to use SQL to control everything, from the engines and compute I'm using to the statements I'm running. But for us, SQL is kind of where it starts and ends. So you should be able to do everything with
Good,
SQL.
because we actually have another question here specifically on SQL, in terms of sort of what do we support in SQL and what dialect do we speak? Can you elaborate on SQL in Firebolt?
So we started by going after Postgres, and then we evolved it into Presto and Athena, and we're planning to add more and more into it. The reason is that in many cases, people just don't directly write SQL on Firebolt. They use something to work with Firebolt. It can be a BI tool, like a Sisense, Tableau, Looker. It can be a DBT. It can be many things. The important thing for us is to support different dialects so that we can speak to the ecosystem properly. So that if you're using your tool that already generates SQL, that already runs on an existing data warehouse, then you can just switch to Firebolt, have the same SQL running, boom, no effort. There's so much pain in migrating, and data warehouse vendors have been kind of happy about it. Like, getting a unique dialect means it's hard to migrate. But then, and again, we haven't invented that, so it happens all over the place. You want your dialect to be more flexible. You want it to support different from Postgres to Athena to other things. So yeah, so it's formal, yet it's actually supporting multi-dialects in SQL.
So yeah, it started with at the core, it's a Postgres dialect, but to make it as compliant to other query engines and warehouses out there, to make life easier for your.
By the way, we're supposed to release Looker soon. Our native driver for Looker, SAS online. It covers almost 100% of the SQL that generate there. We're super proud of it. Like, the amount of pain and suffering we went through to support that SQL coverage on Looker, passing Looker tests, passing Looker formal kind of compliance is big for us, and that's exactly the thing.
Yeah.
Making
So,
SQL.
just clarification for the audience here: we do support Looker via JDBC today, and literally any day. Also, the Looker Cloud version will have its native connectivity to Firebolt.
Yes.
Maybe one final question. There's an interesting question on streaming. So, where does Firebolt stand on streaming, Kafka, Kinesis, things like that?
So for us, Kafka and S3 are equally important, and that's kind of how we look at the world. Like, we assume you either use S3 or Kafka to stream data into Firebolt. So Kafka, which is in beta now, is going to be released soon, meaning that you can create an external table or a pipe, actually, that is Kafka driven, and you just stream data into Firebolt. The nice thing about it is, it's for the first time, you can actually connect streaming to warehousing. You can actually say, I can take my Kafka streams that can, spike up and down. It's a stream, and I can connect that to Firebolt and avoid staging on the lake. Avoid using S3 and all of those intermediate staging to get Kafka into a warehouse. So you get this near real-time operational time series level experience on one hand. On the other hand, you can run OLAP, heavy scans within the same environment, within the same SQL, and within the same tool. So, and that is something that is very, very unique about Firebolt.
This is great stuff. I think this is it, Eldad. It's time to draw a nice
Take 10
thank
more
you.
questions.
A nice thank you on the board could be a nice finishing touch.
Maybe we can redraw the.
Let's see you do that.
Doing that.
Beautiful, beautiful. Okay.
Thank you, everyone. Until next time.